for having me here. It's a great pleasure to be here. And so today I will start, because in the title that I gave, there is this class SK and maybe a lot of unknown words. So today, and also I guess the next time, we will try to just talk about something that maybe most of you know, maybe I don't know who is a student and doesn't know. So Abhijit told me that students maybe don't know much about supersymmetry. So, okay, I will assume some things, I will say some things. You can just complain if you don't know what I'm talking about, and we see, we will make it interactive.
Even one faculty doesn't know too much about supersymmetry.
Okay, very good, very good. So please, complain if I write something that doesn't make sense. Because also for me, sometimes it's very hard. It's like, what is my name? I can just tell it to you. So please just stop me. So let's say the goal of today would be to learn what is this class S thing. In a concrete way. And even before starting to address this goal, let's say some general things. First, about supersymmetric theories. And let's really say from now on, we forget all dimensions and we are in 4 dimensions and we want to study that. So, first of all, there is n equal to 4 super Young-Mills, which is the best theory in the universe, in the sense that, I mean, I think it's very, very fair to say that it's the theory that is being solved as we speak. And there are very impressive results, especially because of integrability. It happens to be integrable. You will mention a little bit. So maybe the only thing I should say here, okay, maybe I will write the field content. So there is a gauge field. There are 4 Weyl fermions in this theory. And then there are 6 real scalars that if you want, you can also put them together in an asymmetric 4x4 matrix. So this A is the fundamental index of the SU4 symmetry of the theory. And also, if you wish, SU4 is almost like a SO6. So this is how you can also rotate these 6 real scalars. And this theory, because the symmetry is so much, first of all, that's the only massless multiplet that is allowed purely by supersymmetry representation theory. There is nothing else that's allowed. So no matter multiplet exists. There is no way to... So first of all, you can write down a Lagrangian that I'm not going to write down. And you can do your Feynman diagrams if you are very powerful and discover to whatever loop you can do that this is 0. And there are, of course, arguments that the beta function is 0 also non-perturbatively and to all loop orders. And this was a business in the 80s. A very nice result. And not only that, but there is also no possible way, also this is related to the fact that there is no way to write matter multiplets. There is no way to turn on a mass, so there are no relevant operators you can add to this Lagrangian. And this all of this thing, you can understand it now in a modern point of view purely by studying superconformal representation theory. I am not going to do that. I'm just telling you these very basic things that maybe it's good to know. And okay, if you're a student, maybe you can catch me afterwards and ask me what is, or maybe what is a relevant operator if you don't want to ask now. Yeah. So then the next, so maybe, okay, maybe here before I go to the n equal to 2, here as a teaser, I will write n equal to 3, because when you first learn your supersymmetry class, at least when I first learned, people told me that there are no n equal to 3 theories, because they told me that if you write the n equal to 3 vector multiplet, you have to add the CPT for it to be good, and then it becomes n equal to 4, so there is nothing for n equal to 3. But you should never say these things in physics, because then you end up being wrong. So Iñaki, a couple of years ago, he found that it's possible to construct non-Lagrangian n equal to 3 theories, and this, of course, evades this idea that you need to have only the massless vector multiplet. So let me just say that there is this thing, and also the big hope is that maybe with the tools that we will develop for n equal to 2 theories, maybe we can even try to use some of them to learn, because this is something for which we don't really know things, and anything you can do is a paper, and it's great. So, yes. So n equal to 2. Yes, n equal to 2. So first of all, this is where we, so this class S, it will be a big class of these n equal to 2 theories. So first of all, let's start by saying, let's start by writing the field content. And I will write it in this nice way that I like. So here I said that SU4 has this, n equal to 4 has this SU4 R symmetry. N equal to 2 theories have an SU2, and let me put a big R here, times a U1 R symmetry. So little r will be the charge, the U1 R charge, and capital R will be the Kaltan of SU2 from now on. And now let me write so this is the vector multiplet, the n equal to 2 vector multiplet. And maybe you can see that this is 0, and also here, this is 0, little r symmetry. So first of all, here, what we see in this multiplet is that the fermions, they form a doublet under SU2. And this I is the SU2 index that goes from 1 to 2. And in this and there is a scalar that, by the way, if everybody is in a vector multiplet altogether, they all have to have the same color indices. So if this guy is in the adjoint, everybody is in the adjoint. And here I can pick, so let's write in the adjoint representation of the color group. And to be honest, for these lectures, you can just think that it's SUN and that's it. And maybe even SU2 will be more than enough for most of it. And this is the hypermultiplet. That's, okay, it's just a name. And these fields are allowed to be in any representation R of the color group. And what is important to remember is that there are these two fermions that are charged under the U1R symmetry. And there is this doublet of scalars, the squarks. And maybe let me also make some names. Because you see already, this scalar is in the same n equal to 1 chiral multiplet with this fermion. And the same thing goes here, but I have a bar or a dagger. So dagger is equal to bar in these lectures. So this is an n equal to 1 submultiplet, and this is also an n equal to 1. And the same thing happens here. This is an n equal to 1 vector, and this is an n equal to 1 chiral. So this is all you need to know about how to make, so this is the only thing that is allowed from representation theory, and now I need to combine it to, so I didn't do anything, I'm reviewing very basic things. So this is where we are.
What is these arrows?
Please.
On R?
It's just that this is 0 and this can be maybe 1, so it just goes down.
On R, capital
So R is the Cartan of the SU2, so it can have, I don't know, half maybe, and minus a half. That's why I put the arrow backwards. But this is all convention. You can flip the arrows, it's just some convention. And the same thing here. Good. So, yes, please.
Are there no examples of non-Lagrangian equals?
Not as, no. So, okay, good. So what is right now the current knowledge is that n equal to 4, you pick your G and you write down your Lagrangian. If you discover another one, you become famous. There is, yeah. No.
Like, for example, this n equals 4 can be obtained by putting 2, 0 and 6 dimension on a torus.
Yes.
That kind of makes this unique after choice of.
Yes, I will say that, but yes, I think so. But you see, this is a good question for the bootstrap people maybe to answer. And up to now, the whatever bounds they are drawing and what they are doing, it shows only these things. Okay, maybe there is another thing to say. Maybe there can be exotic n equal to force, because the question that these people are asking, so there is one. Okay, this is only for you because, okay, very few people. There are these chiral algebras, and by now it looks like there are a few more chiral algebras that you could write down than the n equal to 4 we think we know, but that's really a completely open thing. So there might be some exotics, but.
And that might have some consequences for.
It will have, yes.
Does the superconformal representation theory say that there is going to be an exactly marginal operator?
Yes, of course, yes.
So in any n equals 4, whatever
Yes.
it is,
Yes.
it would have some direction.
Absolutely.
It may not pass through a free point, I guess.
Yes. So now here, because we have these two different multiplets, first of all, the beta function doesn't have to be 0 if I put them together. There is... can I cross the line a little bit? It's very little. So this is whatever, when you take the two generate, so, okay, anyway, for the SUN that I am gonna talk about, this is n, and for fundamental representation, this is a half, and that's all you need to know in life. So this is what happens. So clearly here we see that we have, depending on what is the number of, what is the color group and what is the number of hypermultiplets we put in, we can have a conformal theory, we can have a non-conformal theory. So there is already a big landscape. And of course, and this we will come to it towards the end of today or tomorrow, there are also non-Lagrangian theories that we cannot even try to describe in this way. And we will see how this happens. So there is a huge landscape. And this class says that we want to learn what it is today. It is part of this landscape, but clearly we have no idea what is outside that. There can be many, many things. And in some sense, you can say that even these things, they are already n equal to 2 theories that are outside. So this is very good. And maybe another thing that I should say as a basic. So the moment you know how many hypermultiplets you have and how many vector multiplets, there is only one piece of information that you need to know, which is called the quiver. And out of that, you can write down your Lagrangian, or as we will learn later also today, there are generalized quivers that describe also non-Lagrangian theories. So, okay, and there are, let's just immediately write down examples. So what is this? When you have a blob, this is, let's do only SUN. So when I write a circle, this is an SUN color group, and it comes with its whole vector multiplet. And then a line represents a hypermultiplet. And when I write it like this, it comes in as a, let's say, anti-fundamental, and it becomes fundamental here. So this is a bifundamental, and I use this. And this basically is your favorite n equal to 4 super Yang-Mills theory. Or if you allow for this hypermultiplet to have a mass, the worst thing you can do is you can write down some theory that's called n equal to 2 star. So that's it. Another example is when you just have a color group and fundamental hypermultiplets. This is n equal to 2 super QCD. And if you also, as you see there, pick an f is equal to 2 and c, the theory becomes conformal, and this is what we were doing in our PhD with Abhijit. And some other theories that I will study. Yes, please.
What does this thing in the second one?
So the box means that there is a flavor symmetry. A circle is a gauge, and this is a flavor symmetry. And actually also I will gauge or ungauge things by making a circle to a box.
And the line is always a fundamental?
A line is always a hypermultiplet.
Is it fundamental and anti-fundamental?
Yes, it comes from here with one fundamental index, and it comes there with an anti-fundamental or the opposite. And a note here, because here I have this Q with a psi, and here I have the bar, there is always a field that goes in the one way and another field that comes in the other way. So I always have both. And this means also that these n equal to 2 theories are non-chiral. Whereas when we will want to study later n equal to 1 theories, there is the option to have a chiral theory. And this is precisely because of the SU2R symmetry, putting these gadgets together. So good, this was a nice question, so I made a nice comment. And then, in general, today, I want to study this type of theories, which if you look at this formula, they immediately come out conformal, or also this type of theories. So you can make necklaces like this, and these are also immediately conformal because of this formula. And this is more or less, if you learn how to use with this, how to play with this, you will have a very good understanding to start playing with classes K. So these are the basic Lagrangian theories which you use to create all the theories you want to play in class S. And maybe, so these are conformal, as I said. And especially, I mean, this was always, people were, Nekrasov was saying always in the paper at the beginning, but especially now the bootstrap people say this all the time, that let's really start understand our conformal theories, and then we will just deform them with a relevant deformation, and then we will be able to obtain any n equal to 2 theory we want as we go down with the Argyve law. And yes?
Notation thing that's confusing.
Yes, please.
You had each hyper you said contributed half.
So the TR is half, and then the number of hypers is here in the front.
Yes. So to get a conformal theory, you want the number of hypers to be twice n?
Yes. So out of each circle, two things have to come out that will end up with something that is an n. So this is, for example, the most basic way you could draw this.
I see. So that NF has to be 2n for.
Yes, precisely, yes. I think this is totally standard notation at this level. Good, so if this is good, we delete this part of the blackboard. And okay, here, maybe because of this statement that I made, it's worth, I don't really care about it for these lectures, but it's maybe very good to know. And maybe I can even phrase it as a theorem, although it's, you know, like a physics theorem. So basically, if you know your representation theory for n equal to 2 superconformal algebra, you know all the possible marginal and relevant operators that you can write down. And let me write here n equal to 2. And what are they? This is very important because, so, first of all, okay, I will write here what you will write if you have a Lagrangian. And I will write here also the superconformal multiplet. Okay, maybe this is something that people will not immediately like if they are not used to it, but okay, it's good to start like so. The marginal operators, they will be descendants of, if you, so what I'm writing here is only if you have a Lagrangian theory. So trace phi squared is the simplest protected operator you get by representation theory alone. So the multiplet in some notation of Dolan Osborne is called like this. But what does it mean? The primary operator has this conformal dimension. This is the U1 R-symmetry that I said at the beginning the n equal to 2 theories have. So this is the BPS condition. And Down in the multiplet, there are these operators. They have precisely conformal dimension delta equal to 4, and they are protected. So in this case, R is equal to 2. And these are precisely the marginal deformations that an n equal to 2 theory can have, and that's it, and there is nothing else if you want a marginal deformation. And there are the relevant operators. Yes, please.
In the vector multiplet?
Precisely, the adjoint scalar in the vector multiplet. And remember that it had this U1 R charge, and it had also 0 as U2.
So basically this is a statement that the gauge coupling is the only marginal.
Yes.
So Q to the 4, can you say how is the singlet made?
And you have to do the appropriate. So I don't.
Q's as well as QR's.
Sorry. So very good. So maybe this is good. So, or here I maybe write it. All the Q bars kill these gadgets. So this is the definition of what is this multiplet. And this is precisely the BPS condition that is obeyed. So if you know these things, you actually know everything about these multiplets.
Because there are only 4 Q's that don't kill it.
Precisely. And these are the ones that I use to raise to make the multiplet. And yes, please, yes.
Q to the power 4 raised pi square. I mean, I didn't quite understand what that is. I mean, this is supposed to be dimension.
So this is an operator, yes, and I act with these guys. Delta has dimension half, so 2 plus 2, 4.
Q has dimension half.
Yes, the supercharge. Why? Because
Oh, Q is supercharged.
okay, I am sorry, but this we will never escape.
I got confused with this one. I'm sorry.
Oh, yeah. So, yes, we will never escape. If I had the option to make math frac or something, I would do it, but not on the blackboard, yes. Sorry for that. So let's put a stupid index here to never forget that it's a supercharge. Thank you, yes. And okay, now here I will make things more confusing because what are the possible relevant operators? They are when we write, so now I will really make it more confusing because I'm already using now superspace. So Q tilde, they belong in a multiplet that I will write now. And these objects are the only relevant operators that we can have in an n equal to 2 theory. And that's a representation theory statement. And these are some multiplets that are called B1. They have the property that delta, so let me write like this. Delta is equal to 2R. So delta is equal to 2. This is the operator, and this is what I write to make it Lagrangian. And they have little r equal to 0. And now, by whom they are killed, maybe I make a little nice space here. So they are killed by Q1. Okay, this. And they are also killed by the 2 bar supercharge. And in fact, there is an SU2 triplet of them. Are there questions? Because now there are more Q symbols. So now when I write this thing, this is a superfield that has as its components the little q, which was the upper component of the SU2 doublet, plus theta psi, plus some auxiliary field theta squared. So I'm sorry for these q's, but there is no way without LaTeX to make it better.
So that's it. So the primary is in spin half of SU2.
Yes.
And
So the q by itself is spin half. So let's write like this. R of q is equal to 1/2. So when I write q tilde, q, this is equal to 1.
Q tilde Q is equal. So
So Q
primary is
tilde-
spin 1 of SU2.
Yes, let's write a little bit slower. Very good, okay. Let's really explain these things. So, I wrote that there is this doublet Qi, and I wrote it like this. So, bar is complex conjugation. So, this means that this gadget has a half R, and this has minus a half R. But then Q tilde has also half. So then when I put them together, I get 1.
Good. So there's a multiplet
Yes.
formed from the bilinears of this, that is, it's spin 1 of SU2.
Mm-hmm.
And the primary has delta equals 2R. Now, R, for that R, should I be putting 1?
Yes.
Okay, so the primary has 2. Delta equals 2.
Yes, precisely.
Okay. And now, acting on it with the supercharges, which themselves transform and spin half of SU2,
Yes.
the spin half part of it is annihilated. Is this right? And the spin 3 halves part is not annihilated.
Yes.
Okay, good. And the term in the Lagrangian was,
This is like here.
but in terms of the primary, what combination of Q's on the primary?
So very good. So now I am doing something. Okay, so here I am using superspace already. So this is not going to. So when I do the theta integration, it's not going to give QQ bar as two scalars clearly. It will give something bigger. So it is equivalent to acting with two Q's on this primary and picking up a descendant in this multiplet.
Right.
That's what it does. So one example of this descendant, so I am beginning with this QQ tilde. One example will be psi bar, no, psi tilde.
I'm trying to understand the SU2. Is the term you add to the Lagrangian, what transformation does it have under SU2?
So this one has SU2R symmetry indices. So of course in the Lagrangian it has to in the end be a scalar.
So basically the Q takes, the first Q takes it to spin 3 halves,
Yes,
and the second Q takes it back to spin 1.
yes.
Okay, I understand. Thank you.
So, but why spin 1 good? You want to go to spin 3 1?
Well, you could break some of the R symmetry if you're turning on a regular problem. It's not a much.
So good. So the statement is that this, the way I write it,
No, but
is the only thing after doing the theta integral that is SU2R symmetry invariant.
yeah.
And that's the only thing I can write down.
Oh, so then I didn't understand. I thought so then the term that you should add to the Lagrangian should be an SU2R symmetry singlet.
Yes.
I
So
don't-
this has SU2 spin 1, and this one also has,
if we just think in terms of forget superspace for a moment.
yes.
Think in terms of supercharges. This is why I was asking you. Was the null state condition that when you take the spin 1 and act with the spin half Q's, that it annihilates the spin half part or the spin 3 halves part?
I think 3 half.
3 halves part. Okay.
Okay, sorry. I said the opposite. Yes.
Okay, so it annihilates the spin 3 halves part. So you keep the spin half part and then the next guy lowers it back.
Yes.
Okay, and why did the Lagrange? Was it necessary that it had to be an SU2 invariant?
So I define my n equal to 2 theory as the theory that has an SU2R symmetry, if you wish.
At the conformal point, that's necessary,
Yes.
but relevant deformations could break that, right?
Yes, but then I will not know for sure if my theory will remain to be an equal to 2 or not. So to be sure that it's an n equal to 2 theory, I want to keep my SU2R symmetry.
See, this I don't understand. What is the connection between having SU2R symmetry and being n equals to outside superconformal?
So just the fact that the n equal to 2 superconformal algebra has this SU2R symmetry, and also the n equal to 2 supersymmetry algebra has the possibility for this n equal
That's the
to 2.
possibility, but it's
Yes.
also the possibility of not
So
having.
yes, so for example, if you go to the Higgs branch, you break it, and we know that. But if you don't go to the Higgs branch, all the examples that I know in my life, they have the SU2.
Okay, I'm not familiar with this example, but
Mhm.
for instance, in Matter-Chern-Simons theories, it often happens that the superconformal point has a certain symmetry,
Mhm.
and then any massive deformation you turn on breaks that R symmetry down to something smaller. That could have happened here, but you're saying
But
it just doesn't.
It doesn't. No.
The only relevant operator by representation theory happens to preserve SU2R.
Yes.
This Q tilde Q has R symmetry spin 1.
Yes.
And this theta integration is equivalent to acting with two supercharges. Is this right? Yeah.
Yes, this is correct. But it's a precise, it's a specific linear combination of Q1 and Q2.
Yes. So the first one just keeps the spin half part, kills the 3/2, and the second one kills the half and gives you a singlet.
Yeah.
This is right.
And the QQ tilde by itself, as an operator, is a short operator. So it's killed by the action of Q that makes it spin 3/2.
Oh.
So you cannot take the QQ bar and make it spin 3/2. That's just zero. That's a null state. So the only thing you get when you act with one Q is the spin half.
Yes.
When you act with second Q is the spin.
Yes.
Yeah. So this is protected so that 3/2 is 1.
Yes.
Yeah, it was just zero to start. Yeah.
So representation theoretically, what is one looking at when one wants to find marginal relevant operators?
So
Is one
you
looking
you
at the
you
top component of
you,
the
you
business
begin.
case?
No, not the top, right?
Bottom side.
Yes, some lower down. So you begin and you basically you know the classification, all the possible short ones, and you start looking. Can I find a delta equal to 4 in this case, or a delta with your
So
fingers?
not anywhere, right? Not anywhere.
So they have to
Because of
have the correct charges, and it should be somewhere. Yes, for example, here I act with 2, here I act with 4.
No, but is it that, does it have to be the bottom of this diagram
I think it has to.
because of the supersymmetry?
Yes.
Yeah, I think so. It's basically that you want to determine the Lagrangian so that if you act with any supercharge on it, it's a total element.
Yes, exactly.
Which is basically that.
Yes, exactly, exactly.
The bottom, up to the fact that if it's a short representation, the bottom is.
Yeah.
More questions? Okay, good. So this is what I wanted to say for n equal to 2 theories. Of course, whatever on Friday or maybe even on Monday, I will talk about n equal to 1. But all of these nice things that we have here, they are not really going to go much through, apart from one thing that maybe I start saying now. So maybe let me state this as a fact, and I will explain a little bit later down because I want to say something else before. So, okay, there is this class S that we will try to discover, but a very good way to obtain.
Can
Yes,
I ask you a
please.
Stupid question.
Yes.
You might naively have thought that you can add superpotentials preserving n equals 1, but not n equals 2.
Okay, let me say this maybe. Very good. So, very good. So, n equal to 2 supersymmetry, and in fact, when I say n equal to 2 supersymmetry, I always think of the SU2R symmetry allows for only one possible superpotential. And this is this. Where now a new object appeared, so QQ tilde are the superfields for the hypermultiplet. Phi is the n equal to 1 chiral that has one of the two so that's the only thing that is allowed.
And presumably Foster knew with a particular coefficient.
Yes, let's say G, and supersymmetry, SU2R symmetry will make this be the same as the G Young-Mills that will appear in the kinetic term.
Okay. So this is now. So the mass term is not a superpotential.
It is a sort of superpotential type, and you could also say that it looks very much like take this phi and put some constant matrix, and it will give something like this looking.
So the mass term should be thought of as going off on the Coulomb branch.
That's one way to think about it.
But is there an independent way of thinking of? I'm sorry to ask again, but you say that there is no way of writing that as just a genuine n equals 1 superpotential that will preserve n equals 2 supersymmetry.
Sorry, this is also n equal to 1.
This is n equals 1, but does it and it preserves
But
n equals 2.
it also preserves the SU2R symmetry. And the same thing is for this gadget. So this gadget, to see that it preserves asymmetry, you have to do one more step. You also have to write down the kinetic term for the Q's that has the V, And there you can check that they both together preserve SU2 asymmetry.
Sorry, I'm getting confused about the utterly elementary. But I had thought that the n equals 1 superpotential is completely fixed without ambiguity by the fact that the theory is n equals 2.
Yes.
So how come you have the freedom to add something else? and
Because
preserve n
this is
equals
by itself SU2 scalar.
2? But is this contradicting what I first said, that the n equals 1 superpotential is true?
Yeah, it is this, but there is a mass, there is possibility of mass term also.
So that's a new term in the n equals 1 superpotential that you
Yes.
can add
Yeah.
that preserves n equals 2. So what I said that the n equals 1 superpotential is completely fixed was not right.
So apart from this.
Yeah, that is the ambiguity.
Mhm.
Okay.
So if you don't add this also, you are trying to get a conformal theory more or less, and then you add this and you break.
Okay.
This is slightly different than Chern-Simons.
So one question.
Yes,
So
please.
So this is part of the Lagrangian, right? What you call Lagrangian?
Yes.
This one here, because it couples to G on this also.
Yes, yes.
Now if I take that operator act with a bunch of Q's, how will
Which
I get?
one? This one or this
No,
one?
no. If I the Lagrangian you say is Q to the 4 acting on
Yes.
pi squared, right? There.
Oh, here,
Yeah.
yes.
And now if I do that and compute the Lagrangian, how
Mhm.
can I ever get the multiplet?
Very good. So this gadget, okay, this is good. So when you want to construct your Lagrangian, you don't really usually do it like this, but let's do it. When you act, you will get, for example, things that they look like this. So what is this? This is the F term from acting
fine.
here twice, so you will get.
Yes, okay, thank you. Yes.
And so on. More? Okay, good. And I wanted to say something else. Okay, very good. A very good way to obtain straight n equal to 2 superconformal field theories is to do something that is called orbifolds of the n equal to 4 theory that we said is very nice because it's basically a unique theory up to the choice of the color group. And we will come back to that.
Just to make some of these discussions be a bit more clearer. So if we take just a hypermultiplet and gauge it,
Yes.
then we have to have that kind of term.
Yes.
Now we can understand that mass term for an ordinary ungauged hypermultiplet as first gauging it with some vector multiplet, giving a
Okay.
web to this 5.
Yes.
Then,
Very good. Yes, that's very
so
good.
that's
Yes.
the only way in which hypers can get.
Perfect.
Thank you.
Yes, perfect. This is very good. Yes,
That's
yes.
the extent
Yes,
mass.
yes, yes, yes. Perfect.
Superspace. At least in storytelling.
Okay, I delete and then I start with something else. So I want, because I will eventually introduce Cyber-Witten curves, and I want to use these as the objects with which I will introduce class S. I want to first say what are supersymmetric vacua, very quickly. So, okay, so now I will write the potential actually. Okay. So we can have phi's and we can have q's. So, and let me schematically say that that's what we do, right? And I will get terms like what I wrote before when Abhijit asked me. So this actually what it is, it's a triplet object in the plus component and a triplet object in the minus component that I got from this little calculation that I did here. And there is also the
So what M?
yes. So M plus is this, M minus is with bars, and this gadget is the other combination. So there is also a term that looks like this. Please, yes.
Sorry, just immediate. This 5 bar, the R equals the spin 1 and the SU2. So there's some sense in which it's annihilated by 6 supercharges. Because you were able to take just 2 supercharged descendant and have that term.
Sorry, can you say again from the beginning? Who is this?
The guy that you used to make your master.
Uh-huh.
The primary, you acted on that primary with 2 supercharges,
Correct.
and that was completely supersymmetric. So there's some sense in which the primary itself then is annihilated by 6 supercharges.
Okay, the truth is, so I cannot immediately answer with a yes that it looks like 6, but the truth is that this multiplet, specifically that has only this QQ tilde, is even, so it is super, so you even have this very short anyway, half BPS, and then you even delete some states there.
Yeah.
And for example, one of the things that is important there is when you act enough, you even get a state that is an equation of motion for the flavor current. So you really, okay, in Dolan-Osborne notation, you put a minus. So maybe this is what you are saying.
I think it must be that there is a
Yes.
sense in which,
Yes.
because the term in the Lagrangian has to be annihilated by all 8 supercharges. There are 2 explicitly, so that takes care of
Yes.
2. But the remaining 6 just have to
Yes,
annihilate it by
yes,
itself.
yes, yes,
So it's really very short.
yes. And yes, it's less than half BPS,
Yeah.
let's say, yes.
The Lagrangian
Yes,
was
yes,
half BPS.
yes, 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 yes.
That's why you acted with 4.
Yes, 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 yes.
Now I'm also confused about what I said, the 3/2 is taken and half is there. Because I remember the shortening condition for this B-type multiplet is actually saying that the lower spin component is killed. Acting by supercharge.
Lower spin in R symmetry.
Okay, but because there is a triplet,
No, sorry,
the,
sorry, I'm totally confused. now.
okay.
That wasn't. Yeah, this is the semi-shortening condition, right? That
Yes.
we obey.
Typically in R symmetry, the higher guy is killed, and in actual
Yeah,
spin, the lower
spin,
guy is
in the
killed.
spin,
Yeah.
yes, but this was scalar.
So it's just the R symmetry, the higher.
No, I think the condition was that
So
for
the
the
point,
scalar fields, the condition was that
the point is that you need to use a Q and a Q bar. One of them you pick to have R symmetry 1 and the other R symmetry 2, or you can do the opposite, right? And that's how you see the whole triplet. Maybe this is the question.
no, I'm just wondering what is the shortening condition for this B multiplet.
For the QQ tilde.
Yeah.
Yes, so it's one Q with R symmetry, let's say 1.
Q's have to kill it, right?
So 2 different Qs.
Oh, there's no level 1 null
Yeah,
state?
there's no level 1.
So there is this.
Oh.
And
That's what I remember.
this. So these 2 things. Or 4 actually, right?
Times, right? This times that, right?
Both. And, yes.
Yes. So nothing happens at level 1.
No, nothing. No, no, no. What happens is that, good. So here, so this is this QQ tilde gadget. Here is the flavor current. And here you start missing things. And here you see this equal to 0. So for example, here there's this gadget that I wrote before there, and so on. Okay, here something very stupid I want to say, very, very simple. So that there is the Coulomb and the Higgs branch. And okay, of course there are mixed maybe, but we will completely ignore them. So we will not talk about them. So the Coulomb branch you obtain if you tell that all your Q's and Q tildes, they are not allowed to get a VEV, and you give, so let's really imagine that we are doing some SUN. So that's how you do it. And why this is good? Because when you put it here with this commutator, this is something that came from the D terms, from the kinetic terms. So everything is 0, and you have a supersymmetric vacuum. And here is the opposite. Okay, you have to set the mass to 0 in order to get 0. This is the mass here. And you also set your phi equal to 0, and you allow to give non-trivial to the hypermultiplets. So when you do this, you break the U1R symmetry. And when you do this, you break the SU2. And again, in terms of operators, because we are very lucky, and in n equal to 2 theories, there is an one-to-one, so the vacua correspond to some, they call it Coulomb branch operators. They are these operators that I wrote before also for any, or let's write R here straight. So these operators, they pick up all the information of this vacua. And here is, so this more general multiplet that I wrote before with delta is equal to 2R. And an example is the example that I gave before with the QQ tilde. So just this. And this is important because later when we will want to do the Seiberg-Witten theory, we will call this VEV something, and we will have it in our equations. And this, you can always rewrite these things as functions of these things. Of course, they might be very crazy, complicated functions if you turn on the coupling constant, but... And another thing that maybe I start say also a tiny little thing about the n equal 2 theories, one that I want to study, is that in general for n equal to 1 theories, this type of thing you cannot do, basically because you don't have, you have only one U1R symmetry and you don't have this as U2 and U1. But for the theories that I will want to eventually study, this class SK, because you obtain them as orbifold daughters of n equal to 2 theory, they have an extra U1, and this allows you to define these things very carefully, actually. So you can there have a Coulomb branch and a Higgs branch and define all the nice objects that you want. Good.
The effective theory is just in non-interacting points, right?
I mean, what do you mean?
I mean, if you go to a particular point in the Higgs branch,
You can have interactions. So going to the Higgs branch, you just replace wherever you see in your Lagrangian Q, you say Q vev plus another Q. But then there are interactions.
but the gauge field is gone, right?
The gauge field is also there. I mean, there are non-renormalization theorems for some possible terms in the effective Lagrangian on the Higgs branch, but for some, not in general.
The gauge group is not Higgs totally?
Depends on what you do, I guess. I think it will be Higgs, but it depends on how you do it, right? You cannot completely get rid of interactions.
You're saying at a generic point?
Generic point. The generic point.
Do you know this? I don't think you can completely get rid of interactions.
What is the condition on Q, on the various Qs? Do they have to commute with each other? So they can be turned on.
So here I didn't say, right?
But they have to wear some sort of superpotential.
So,
zero.
yeah, so you okay, I don't know. I mean, I think this is a choice of what you want to do, right?
Right, but just let's say we're just classical. So you turn on Q subject to the fact that the potential remains zero.
Mm-hmm.
What is the equation that tells you that potential remains zero?
Very good. So this will tell you that the potential remains zero. So all of these things, they will have to, very good. So you have to go and pick, very good, good. Okay, now you will make me solve things, but you have to make a choice, for example. For example, this is a choice. And of course, you could put, always remember that here there is a whole SU2 that can make the more general thing. So, but this is good enough, right? Very good. So, and then you have to do the same thing for the Q bar. And you have to make another choice such that this thing is always 0. So this is QQ tilde. So I never wrote what is Q bar. I think it's this. No. In fact, it's this. So it's this. So if I make now, for example, this choice, I think I am guaranteed to make this 0 and this 0.
And this is, there's a color index also here.
Yes, of course, yes.
So those cues can be completely independent in color?
So I think usually you will want to make some way diagonal something, right?
So let's say the first cue is in the 1 slot, the second cue can be in the 2 slot. That's what Abhijit was saying, that if you have, since you have enough cues, it will completely break down the gauge loop then.
If you make them all non-zero.
Yeah.
This is very possible, yes.
Make the first guy 1,
Yes,
second
yes,
guy
yes.
2,
This is
third
very
guy 2.
possible.
Yeah, but then now that the gauge fields are gone, the only the massless guys are essentially.
Okay, but you have to write now an effective Lagrangian for them, and things can happen. There are non-renormalization theorems for this Lagrangian, but it's not that it's nothing.
I'm sorry, a remedial question.
I am really not going to study
Okay,
Higgs.
so
I am
let's
only
say-
going to do. Oh, let's ask one last.
Okay.
Yes.
We can do it later.
Okay. Okay, good. So now I want to introduce these orbifold constructions. And especially because it will be completely important when I want to do my n equal to 1 theories, that I will get as an orbifold of the n equal to 2 ones. So let's do this now slowly. Good. Okay, for this I need to throw in some words also from string theory, but super minimal. So first of all, the n equal to 4 super Young-Mills, and let's just do SUN and be done with no other complications. We realize it on a stack of ND3 branes. Is everybody okay with this statement? Good. So now I want to take this theory and do something to it. Maybe another symbol. So this is where the D3 brane lives. And in fact, here you see these are the six real scalars of n equal to 4 super Young-Mills, and they are rotated by the SO6 symmetry. And now I do the following to break supersymmetry. I add here some type of singularity, and I want to look only at one very particular one. So let's take this. I want to do this type of orbifold. And by doing this identification, this space starts looking like a cone. So this direction, one of the, whatever, a radius picked out of these directions will be the cone, and here I will have an S3. So now we can stupidly count our bosonic symmetries to make sure that we are doing the right thing. Here there is an SO2, which is the U1R symmetry of our n equal to 2. And here we have this SO3, which is the SU2 R symmetry of Rn equal to 2. You can even count the supercharges, and in fact, for some calculations, you have to do this counting very carefully. So you begin with the 32 supercharges of type 2b. Because you put the D3 brane, you have to write conditions of this form, which break half of the supersymmetry to the 16 supercharges of n equal to 4 super Young-Mills.
So you're saying of that SO4, SU2 is preserved to make this orbifolding?
Yes.
Not U2?
Yes. I think it says U2.
I see.
I hope I'm not missing something, but I think it's just yeah.
Sorry, does it matter that you've done e to the power 2 pi IL and e to the power minus 2 pi?
They have to be the opposite.
Opposite.
They
That's
have to be.
important.
That's important for the preservation of supersymmetry, actually.
Yeah. I think if it had been the same, it would have been the same problem as, you know, it would have then been U2. It's like the Calabi out.
Yes, I don't know what will happen with supersymmetry. Then I would have to do again the yes, yes.
This X was the commutator of the scalar field.
Who?
The X was the commutator of the scalar
Sorry. When I write this, I mean.
Z.
Oh, okay. Yes.
Okay, maybe by something. Yes.
So really,
Yes, please.
the boundary you write as S3.
Yes. I mean, okay, this is schematic also. I just want to say.
That should be lens space.
Yes,
right?
yes,
S3
yes,
mod.
yes. So, but anyway, this also is schematic. I just wanted to make so that we need to pick radius, and this is why you don't have 4 anymore, but you have 3, and this is where the SO3 is.
Because if it's S3, then it
Yes.
would be SO4.
Yes, 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 yes. This is very schematic. Yes. Very good, thank you. So this is how you count, and then when you have this orbifold, you have to write also a similar type of condition here with this 6, 7 and this 8, 9 gamma matrices, and this breaks to 8 supercharges, so that now you have n equal to 2 in 4 dimensions. So this is also the supersymmetry counting.
Another thing to see the single SU2 instead of the two SU2s is that initially when we have S3, the symmetry group was SO4 or SU2 times SU2, and you take this ZL e to the 2 pi I by L and
Yes.
complex conjugate as the Cartan of one of the SU2s. That SU2 is
Very
more
good.
than many.
Very good.
No, but it's precisely that I was doing. So the whole of the second SU2 is preserved, and then the Cartan of of the first SU2.
So the way it works, okay, I remember this by heart. We can try to do it.
Yeah, that's why it's
Is
something
that-
giving SU2 can be.
So from the full thing that you have, so you want to say that it is what?
No, I'm getting an extra U1 when I calculated. Exactly, I was doing exactly what Naveen was saying. He was saying that this rotation here is a rotation. Suppose you think of SO4 as SU2 times SU2.
Yes,
Then this rotation is with J3
yes,
in one of the two SU2s.
yes.
So the whole second SU2 is preserved, but I would have thought that also the J3 rotations of the first SU2 was preserved.
So I want to claim that this is not the case unless you pick a Z2 orbifold where in fact there is a whole SU2 extra.
I see. I'm probably doing something.
Yes.
But do you see what I'm saying?
Why is that Cartan preserved after you?
Because any rotation that commutes with this element is preserved. J3 commutes with this.
Okay, I don't see. I don't see how you can have an. Okay, maybe we can write also the.
I'm
La
probably doing something wrong.
Yeah, yeah, yeah. I mean, also we will write down the Lagrangian, so we can look at the Lagrangian.
Yeah, but this is just a geometrical question within SO4. Right?
Correct.
There's a particular discrete rotation in SO4.
Correct.
What is the subgroup of commuting things? It's a simple thing to answer. And you're saying it's SU2 and you're sure.
Yes. So now I want to learn how to write down the Lagrangian for this thing. And how do I do it? So so of course, I mean, already you can see here what is going on. These are the scalar fields of n equal to 4 super Young-Mills, and they have to obey this equation. And in fact, you can write a similar thing, because we know that we need to obey supersymmetry, you can write a similar thing for any field. So let me first write a schematic. So if you have a field, you need to impose the identification with. So first of all, this thing, you can view it as an element of the archimetry that acts here. And you have to tell me, for each field, first of all, in which representation of the archimetry transform, and take this element and write it here. So that's homework number 1. Then, this is not enough. There is also, let me first write something. So the fields, they will also be matrices in the color group. So there should be an action also, and I will make a picture in a second to try to make it more intuitive, an action also on the color space of this orbifold. And the action that I will choose is this. And maybe everywhere there should be a 1, which is a 1. So I am doing the following. I have to say more things. So I first think that this field is a Ln by Ln. So I begin with a bigger color group. And this comes from the method of images. Okay, maybe I draw immediately a picture. So if so let's imagine, let's say that this is, I don't know, 8 and a 9. And just for visual purposes, that's not what I want to do, but just for visual, I go a little bit off to the Higgs branch just to be able to draw. So if these were my original ND3 branes, by method of images, I have to draw all of them. Here they are 8. So this is a Z8 orbifold. And in general, when I put them down, stupidly, they look like that there is an SU-LN. However, if you look more carefully, you will see the following. You will see that you can have strings that they stretch between the same thing, and this you should really interpret as a vector multiplet. But then you can have these other type of things. And here, in this picture, we really see that we have SUN to the L. So I am trying to mimic this that I see in this picture naively with putting this extra action here on the color space. And this is one nice element of the ZL orbifold. So I use that one. And I guess here you could even try to use a little bit different ones, but you will have to be careful with what happens in the end. Good. So I impose this condition to all of my fields. And what happens is the following. And one very quick way to do this job is to also keep in mind that everybody, for example, organizes in n equal to 1 superspace, so that you don't have to do the fermions separately. So what happens is that, for example, the X4, 5 is not charged under these things. So basically what you get is an identification just with this action on the color space. What this does to you is that if you have a big Ln by Ln matrix, it makes most of the things 0, apart from here diagonal blocks, which will be now, I will call them phi 1, phi 2, phi L. These are n by n matrices. And this will be the vector adjoints, the scalars in the adjoint of my daughter n equal to 2 theory. The similar thing I have to do, okay, now I delete the picture to write. I need to do for example, the 6 and the 7. And here, what's going to happen to me is that I will have this phase.
So far we were doing 4, 5. Oh, thank you.
So this is the 4, 5, which is the one that is not touched by the orbifold. And here I do one that is touched by the orbifold. And I do the one that is touched positively. So what is going to happen is that now I will get zeros in the diagonal because of this extra phase. But now in the off diagonal, I will get non-zero things. And now these things I will call my Q's of the n equal to 2 theory that I want to study. We can also put some, whatever, L minus 1, L, some indices to separate them. And you see that these objects are by fundamentals that precisely, okay, I think I wanted to have my picture. So these are the phi's. They start and they end in the same one. And the Q's, they start from the one and they go to the other one. And they, in fact, they really have an arrow. They go in the one way. And then I can do the precise same thing for the other ones that are here. These, they come with a minus. So here it will happen the opposite. Maybe I delete this and I write here. So this will be now my Q tildes. And these objects will be backwards. And that's how I make my Lagrangian, the fields. And now the Lagrangian is very easy to calculate it.
Are these all independent? Q1, Q2?
Yes, all of this stuff is independent fields. So, for example, Q1 is the one that goes from the number 1 D3 branes to the number 2 D3 branes. Then these ones will be Q2, Q3, and so on. They are all independent.
But the fact that we're doing the C mod Zn autofold, it doesn't mean that Q1 can be rotated to Q2?
No. So they have different. So, okay, good. Let's start drawing the quiver.
Before you just projected out.
Yes,
all the
it
stuff
made,
except for-
it made all of these zeros. This is what the orbifold did.
And it was parameterized by these remaining independent.
Let's make this picture nicely and the quiver. So, let's say this is phi1. Let's say that this is Q1. This is Q1 tilde. And the quiver looks like this. With L nodes.
The autofold is rotating this diagram. That's not right.
Wait, let's go slowly. Let's go slowly. Let's go very slowly. There is a truth into what you say, but let's. Yes, yes, very good. So, so now I want to make the Lagrangian, okay? So let's.
Can I ask a question?
Yes, please.
Was there choice in embedding of Zn into the gauge group?
Of what? Oh, sorry, building
the way,
what?
The way you embed Zl into the gauge group.
So I think, okay, very good. I think there is a choice in this, but you have to always pick an element of the ZL. You have to pick a representation of an element.
Yeah, but various choices give me various other.
I think they will give the precise same thing. I played only once with this, with one other specific choice, and I got the same. But I have never done it in complete generality.
From the string theory point of view, there should not be any equivalence.
Yes.
Geometrically, what's happening is totally wrong. Everything should be gaugeable.
So what I had in mind, for example, if I instead of 2 pi L over L over there, if I do twice that phase, okay? and
Oh,
I
no, no,
keep
no,
this
wait,
phase
wait.
there.
This, when you write this thing down, this is fixing you which specific action you are doing to the scalar fields. So this specific element of the group, you have to use, it's another representation of the same element, but you have to use this element. So that is not a choice.
I think what he's saying is one could use another something like e to the 2 pi I k by L, where k and L don't have common values. That shows what.
Okay, but
That
that,
will also generate the ZL action.
but do you,
But tau will also accordingly.
yes, exactly.
That's what you're saying.
Why is it? Yeah, maybe why is this locked to tau to this gauge, to the action on the action of the color space?
You know, just from the string theory point of view,
Yes.
intuitively what you're doing is taking these D branes
Yeah.
and separating them.
Yeah.
And then you've got the Zn action. So suppose I was in the plane let's say, one of the planes on which it acts, 7, 8.
Yes.
Okay, you keep some of these branes together, and then Zn rotates these to the next bunch,
Yeah.
and then rotates this to the next bunch. So that action, because this action is moving in color space. Let's say this was 1, 2, 3, 4, 5, 6, 7, 8, 9 up to n. This was the next. So if you shift in color space, you should be also rotating by the same amount. I mean, that's how I was thinking of this.
Yes. 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 I think so.
But this puzzles me then about how you have so many independent fields.
Good. Let's go.
Yeah.
Let's write the Lagrangian, and then so the very quick answer to what you say is that at what we will say is called the orbifold point, where all the coupling. So there is an extra ZL symmetry that allows you to, if you wish, rotate between the two different, all the different fields. This is the answer. But let's see it. Good. And I will do precisely the same thing, most probably on Monday, to give you the classes K theories. So you just do another little different orbifold. So now it's very clear what is this thing. Good. So, okay, maybe very quickly, what is the Lagrange, or the superpotential, all we need for n equal to 4? Okay, let me maybe first just write down the answer. Okay, of course here there might be a factor, but I skip it completely. The way to convince yourself that this is the superpotential of n equal to 4 is that you should think that these are 3 complex scalars, and there is an SU3 inside SU4 that rotates them. So the only possible thing that you could write that has this SU3 sub-part of the R symmetry is you use the epsilon tensor of this SU3, and that's the only thing you can write down. There's nothing else. And the fact that this is the G Young-Mills is if you want to impose full SU4 R symmetry, so that the whatever fermions will come out of here will match with the ones from the kinetic term. So that's how you do the job. So that's what it is. And then we are instructed now to take these big matrices that we wrote down with all the zeros and plug them in here. So what you will get is, this of course is in the front of everything and doesn't do anything. But here you can have 2 things. You can have, and now these objects have indices. And you get a second term, which is from the next color group. That's what you get. Now, at this point, now it's immediate obvious to see that there is this Zn symmetry that rotates between all of the different indices. Okay, and of course there is a sum in the front somewhere. And this, when all of the coupling constants for all of these different things are equal, we call it the orbifold point. But you can now, for this specific theory, go and ask, do I have marginal deformations? And the answer is yes, because we have trace phi squared of all these different i's. You act with 4 q's in front of it. One linear combination of them, when you sum them all with plus, is the original Lagrangian here at the orbifold point. But then there are all the possible ways that you can make linear combination of them, and these are all marginal deformations away from this. So then, if you wish, you can write, after all these marginal deformations, different coupling constants here. And this is this quiver theory in full generality with all coupling constants all different.
Could I ask you, why weren't there strings stretching from one bunch of branes, not just to the adjoining ones, but the second guy, for instance?
Very good. So I think, so this has to be in contradiction with what we did here, right? And you could try to argue that this tau that you use make it to be a little bit different, so that, for example, it shifts the thing up, but then you will spoil the recipe for phi. So if you want the same tau to do the projection for all the fields, and for example for phi's, you have to make, yes.
Okay, I'm sorry, but just naively in string theory.
Yes.
We have strings stretching between any pairs of B-branes,
Yes.
and then the orbifold identification does whatever it does to it.
Yes.
So I would have thought that there would be n independent kinds of strings, labeled by starting with the ith guy and going to the I plus jth guy.
Yes. Generically, yes.
And I is unimportant because that's rotated around by Zn, but the difference is important. So I would have thought that the total number of fields, I'm sorry to be
Yeah.
the total number of fields should have been n fields.
No, but that is what was projected out in this big matrix, right? There's a block diagonal matrix, and the Q entries that survive were nearest neighbor entries.
Yeah, but I'm not understanding. What maybe I'm in a different basis, but in my basis, I've just blown up my things a little bit here.
Yes, like this picture, yes.
Right. Then the Zn action is just a rotation.
Yes.
Okay. So what the rotation will do is identify this string with this string.
Yeah, the Zn action was not a rotation.
Yes.
Right. So
It was a block by block complex rotation.
Yes.
right.
There's one here, e to the I pi, here, e to the 2 pi I pi, here, and this
Right.
one.
So it's going to a different basis. Right. It's like I'm working with the shift symmetry being shifts,
Yes.
and you're working with the shift symmetry being phases.
Phases, yes.
Okay, but let me just move to my basis for a moment because I can see it. Okay, in my basis I have these strings here. Then this string is the same as this string because that just rotates.
Yes.
But this string is different from this string. So I would have got totally n independent fields. One adjoint and n minus 1 bifundamentals. What confused me is that you got more or less that, but you got n adjoint
Yes.
and n bifundamentals.
Yes.
And that confused me.
So the adjoints are just strings stretching at the same node.
They are,
Here to
yes.
here. And it doesn't matter which one they stretch to because they all rotated to each other.
But I think maybe in your basis you shouldn't start with a k with an L times n matrix. Maybe the way you do it, because you just rotate.
I think I want to start with L times n because I've got, let's say, I've got n here. Then I have to have the same here and same here and same here and same here. So I have to have L times n total branes.
Okay, good.
Right. And then these things go. Let's do no projection. Then there are the strings that go from brane to brane, strings that go between branes.
So, but then in your thing, you in fact then get a big NL matrix.
Exactly.
That
Big
they are all
K
like.
and-
So
and
in
then-
fact you get more.
No. And then I have no projection. You also started with a big KL
Yes.
and then you projected.
Yes.
I'm trying to do that in my head,
Yes.
in my basis. So what I'm getting is strings that stretch for each guy like this. I'm getting one string,
Yes.
and then for the adjoint I'm getting one string. So totally I'm getting n different matrix fields. So L different matrix fields. Is that what you also got in some language?
No, I think it's a little bit different.
Because anything that goes from here to here is identified with whatever goes from here to here by Z rotation. You're overfolding by Z.
Yeah.
So this cannot be independent.
So in the way you are writing, okay, I don't know. It looks to me like you have this and they are all the same, but they
Yes.
are all K, so they are all that many. And you have the Qs and they are also all identified,
And
right?
you can go Q here and Q here. And
Yes, very good. But they are also all NL matrices, right?
They are n times n matrices because they're beginning with one bunch of n and ending with one bunch of n.
So we are not doing the same orbifold then, because the numbers are not the same.
How many total matrices do you have?
I have,
And you have all n cross n matrices, right? In the end.
all of them are n by n.
And how many totally?
So I have L of them, L of them, and L of them.
Yeah, the L and the L sound more or less okay. I can't understand the L5. I'll ask you later.
Yes. I mean, we would have to do explicitly to really see the change of basis. I don't know how else to answer this.
It's not important.
Yes.
And also your adjoint is not going to be the adjoint here.
Why
Because
not?
your basis is different.
Right. But in the end, I should have the same number of fields. Yeah.
Yes. Okay, but if you are happy with this,
Sure.
this is the way we do it.
Yeah.
And I will do precisely the same thing for a slightly different orbifold to get the n equal to 1 theories that I want. And okay, if you wish theorem, because all of these descended from n equal to 4, they are all conformal and they are happy. And the same thing will happen for the n equal to 1 theory that I want to study later.
But basically, the way Shiraz is looking at it, these other L minus 1 flies would come from winding strings, right?
Winding where to where?
From ith brane back to the ith brane after, say, some J time.
No, but there are no non-contractible cycles. I thought that was somehow trivial. Unless there's something I'm missing there. Yeah.
Can it be that, so in this picture then you have also,
That basis is very strange. Right?
yeah, I don't know.
That basis is strange. I think this basis is
No, this is the property of this. If you keep adjoint, it will take
Yes.
more adjoint.
Yes,
Because it's
yes,
diagonal,
yes,
right?
yes,
Diagonal
yes.
color space.
Yeah, but if you were trying to
Precisely.
just translate from geometry to physics, you would use my basis, right? I mean, okay.
So now, because eventually I want to start deriving curves. Okay, maybe I completely overestimated what I can say, but it's okay.
That always happens to all us.
We enjoy, we enjoy. So now I want to bring in one more little aspect from string
The thing
theory.
is that had you said everything you planned, we would have understood none of it. At least
I
I would
see.
have understood none of it.
Okay, very good, very good. So, yes, so I want to bring in another little element from string theory, and this is the following. So I want to derive curves, and I will do the most visual way that I know how to do it, which is I will use the Hanani-Witten picture of describing n equal to 2 theories. And this, so I just say now, if you wish, you don't have to believe me, that there is a way you do some T-duality, and I will count my symmetries to prove on the 6 coordinate that I had before. And what I get is the following. So I will get, so here I did something. Yes, please.
Can I just go back? I think it couldn't address the question. Right. The action is the adjoint action on the orbital. Right?
So in addition to the constant mode, there is a constant momentum mode. There's in addition to the zero momentum mode, there is the additional momentum mode in this that you have, and the adjoint action will make it invariant under Z. There are n of them.
But now, sorry, let's fix the counting.
Yeah. So then you have n of them, the
Yes.
5, and similarly q bars will work out. It will be slightly shifted.
And why don't you have them stretched strings? Strings between I and I plus 2?
You will have those. Yeah, you will have those. But,
This is
but-
how
but-
you make my counting then for
yeah,
Qs, right?
But yeah, but then in order to go to this gauge theoretic basis, this is you have to bring everything back to this basis, and then you will see this. Sorry.
Yes, so I just write this down. We can complain if you want, but okay, good. So very stupidly here you straight see the SU2 are symmetry, so this is a nice thing. You straight see the U1, so it's very good. And we can also do the counting for the supersymmetry. So we have 32 to start with, half of it is killed by the D4, half of it is killed by the NS5, and that's it.
And where is the parameter of the orbifold in this?
It is here. So, yes, so you replace the orbifold by a tau nut with how many L centers, and then blah, blah, blah.
NS5s cut the default range.
Sorry?
The NS5s cut the default range.
Yes, I will draw now. I will draw many different pictures. So this thing, let's draw it maybe in let's draw it in this. So these are the D4s and so on. And whatever D4s come out of here, you have to identify them so they live in an extra circle like this. If you want, you can draw this. This is where the NS5 lives. And so on, all of them. And here you can also do the counting of the fields extremely nicely. So, okay, I just say things basically now, and who wants to complain, complains. So, the strings that stretch between the same stack of D4s, they correspond to a single vector multiplet. So this is some phi 2 and all of its supersymmetric partners. And here I have strings that stretch between two different stacks, and these, they give the hypermultiplets, let's say Q2. And the Q tilde is the one that is backwards. And here, by the way, with this picture, the counting that I did is also immediately obvious.
And in particular, you only seem to have these neighboring strings.
Yes, yes. So this is very nice. Another thing maybe to very quickly say is that let's consider only one of these things. So between two NS5s. So I would start writing maybe the DBI action or something. And then, because this is a D4, right? I would have to do an integral. There is the 4 dimensions, and then there will be, I would have to also do the integral of the D6. So if I do this integral, let me be stupid and say that there is a length that I get. I would have, and by the way, here when I expand my DBI, I will have the F mu squared. So this length is identified with the 1 over G Young-Mills squared. So you stop me when you want. And in fact, also when we will want to write everything in a nice supersymmetric way, we will put everything in the complex coupling. So they will go together in this. So this distance here, later it will become the whole thing in a moment when I say something more, when we will uplift trend theory. So these are the main basic elements that we need to know. And maybe one more final thing is the following. So because here we have everything. So when we move things, let's pick one of our D4s and move it in the 4-5, we break the U1R symmetry. And you remember we said that in the Coulomb branch, that's what we do, we break the U1R symmetry. So if I take the D4s and I really separate them, so there is really a distance here between two, this is an A parameter, a Coulomb moduli. And also, I can do the same here. If I pick one of my D4s and I push it a little bit away from the 0, so you can think that I put all of them at the origin. If I pull one, I break the SU2. So this is like going to the Higgs branch.
So it's missing the NS5
Yeah, just
yeah,
yes.
a little bit. Yeah.
So, okay, of course I need to do this in some way, but if I can do this, I go to the Higgs branch. But, so this is the most important thing we want now. And another thing that is maybe very important, when I have a D4 here, I am in the Coulomb branch now, and I have another D4 that is further down. This length that the string will have is going to be the mass of the hypermultiplet.
This was the distance in the 4-5 direction or the other direction?
So this distance is in the 4-5.
So this
Yes.
is the phi q bar.
Yes, 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 yes. But it's between this and this.
Yeah.
And here, yes. So it all makes complete sense. Okay, now I want to do the following. First of all, I want to define some, so let's keep this picture.
So in this construction, the theta angle is 0?
Yes, there is no theta angle. So, but now I will put it now. Yeah, very good. So, I will do the following. I will define V, a complex like this, and this is going to be the one that knows about the U1. And then I will take this x6. I will really think that I am now uplifting to M theory so that there is another thing here. So the D4s will become M5s and they will have a little bit more here. And of course then S5 will also become M5s. So I do this definition. And this is precisely where the theta will come from. And I also write, so these definitions.
Sorry, what was S again, please?
Here.
No, I mean, S was the position of something.
So S will be the positions. So here you see, the NS5s, they have positions here.
So, it's the
So
position
I
of the
had,
NS5.
yes, I had this circle here.
I see. Now I see.
And this, in fact, will allow me to define Q, the exponentiated which will be another way to parameterize coupling constants. And here on this circle, we see that the distances,
So 10 is the circle direction.
so here, this is what came from the T-duality.
Sorry, which of these directions is compact?
So I can open up this, but this is a circle.
Okay, fine.
Good. In fact, if you want here, I could divide by the radius of the, but I don't want to do it. It's okay. Put it to 1. Good. So this is how things look. And this now will be the new parameter for my coupling constants. And so we see here that the distance between these will be the coupling constants. Good, I have, I think, everything I need. Maybe a comment, because we introduced, okay, I deleted already all of the possible parameters. A comment is the following, that if I could for a moment cut here, and let's say we are drawing only a very simple, let's draw this diagram. So only this. What theory is this? So the rule a little bit, and you can experiment.
I'm really sorry. This one is X10 or X6? Where you from?
So this is X6.
So X6
And
is
you
the
should
circle,
imagine
X10
that there is
also-
another, yes.
Okay.
So if I draw it as X6, here I get only the 1 over G Young-Mills squared, like what I said here.
6 need not be a circle. though.
In general, it doesn't be. So for example, here X6 is not a circle.
But then you'll have some
It's
flavor
open.
flavor symmetry.
Precisely. So this is what I want to say now. So whatever is external, they will be it will define parameters that define the theory. And whatever is internal, so for example, this face here is the thing that knows about the Coulomb branch. So very roughly, the rule is that faces, they give you the number of faces, gives the number, the dimension of the Coulomb branch. And the number of external minus 3 because you can shift and you also have to make this thing hold together. So this gives you the number of parameters that define the theory. So it will be masses and coupling constants. And here we see what we have. We have one theory with only one coupling constant and 4 masses. And what is that? This will be the SU24 flavor because I have 2 D4 brains. This is SU2. Are we happy with this? So if we are happy, now I can basically just use this to derive curves. So let's just do it for this picture.
Oh, 10 was the M theory direction.
Yes.
Well,
You
now
want
I
it to be
understand.
called the...
Now I understand. Now I understand. Thank you. Okay.
You want it to be called 11, maybe. No.
It's fine. It's fine.
Yes.
I didn't realize you had seen.
So maybe also...
Oh, so it's the. I see. It's the positions of the 5 brains in the M theory direction.
Yes, precisely. Yes.
Okay. Yes. The M
So-
points.
Now I draw this picture, and I want to put it using these new coordinates that I defined. Again, this is e to the minus s, and s is this x6 plus I x10, or 11, the M theory circle. Put M. And of course, in M theory, now you should think that all of these brains, they become
They're all M5.
and in fact, not just that. So, okay, first of all, let me say one step before I uplift to M theory. So when you draw, if this is an NS5, and this is a D4, when I include the tension for this thing, this is just a classical picture. There is the Maldacena-Callan. So this is going to look like this, like an NS5 that is pinched. So this is how it really looks. So, and then when you uplift to M theory, you anyway have only M5 brains. So this picture, we should really think of it as this. Okay, this is an exercise in drawing. So you have a shape like this. But of course, at infinity, it becomes very small. So that's what you have. So what you have is a single M5 with non-trivial topology. And precisely this shape of this M5 brain, the curve that describes it, is the Seiberg-Witten curve. So there will be an equation. Again, this is the V, and this is the T. No, the T is the other way. There will be an equation, and this will be the Seiberg-Witten curve. Now let's try to derive this. I could right now make an intermezzo on Seiberg-Witten theory, but all the students have left, I think. So I think I can skip it, no?
Also, maybe
We can go to lunch.
at some point. I mean, when it's next.
So now, so one thing I could do, but then I shouldn't do it. There is the Seiberg-Witten intermezzo, and then I would really derive the curve. Should I derive the curve very quickly and maybe just write it and then we pause? So it's actually very, very easy. So let's do it here. So what is happening? Because here I have also everything, all the parameters. So I need to guess some type of polynomial that when I touch a brain is 0. Okay, let's do something very stupid first. Let's go to v to infinity, right? When I go very high up, the only thing I see in my life is this and this NS5 brain. So also I have the freedom to rescale this axis. So I put here 1 and here q. So what I will get is this.
Please remind me again, T was what?
T is here, is e to the minus s, and s is x6 plus I m theory.
Excellent. And V was what?
V this is the u1.
So everything is happening in two complex dimensions.
Yes, precisely.
And one of these complex dimensions is made up of circles, the other one is just not complex.
Yes. So
And
my
because it's circles, that's why you've made it e to the power minus s.
yes,
To make the periodicity.
precisely, yes, yes.
Okay.
So just by looking at what happens up here, I get that it has to start like this for V very large. And then, of course, there will be also something that is linear in V and something that is constant, equal to 0. This is how my curve will look like. And let me actually, because I will need it later, let me call this P1 of T, that is an unknown, and P2 of T. So that's how it should like. Now let's do something else. Let's look what happens when T goes to infinity and when T goes to 0. So now I will view the curve as a polynomial in T. So when T goes to infinity, I will also pick up the leading term. And it will have, because this is the infinity.
That's like x6 going to either minus infinity or infinity.
Yes. I will pick these two zeros, here and here. I will pick this. There will be things here. And in the end, there should be something. Here there is a possible coefficient that I will fill it in a moment. So that's what is happening in life. Now, there is this unknown coefficient, and there is here a lot of stuff.
Why is it that it's quadratic in T?
Okay, very good. So it could be more, but then it would not teach us anything else, because I only need 2 zeros. And here only 2 zeros. So then this is good enough.
Quadratic in T is that there are two NS5.
Precisely, precisely. So T quadratic is how many NS5 brains you have, and the power of the maximum power of P is how many D4s you have. Very good. So now, if I impose that this equation together with this equation hold, basically I fix everything, and let me write the answer. Maybe there is a factor, yes. And there is only one thing that I cannot fix, and that's this. I remain with an unknown constant. Everything else, by putting these two things together, I fix it.
So let me just do the
Yes.
counting if you don't mind.
Yes.
So we've got a polynomial that's quadratic in T and quadratic in V.
Yes.
And also has lower powers.
Yes.
Okay. So now we can count how many coefficients there are in that. So that's some small number of coefficients.
Yes.
And then you have two pieces of data. First, two pieces of data at large V.
Yes.
And you also have
So at large V, it's this and this that I wrote.
wait, at large V it's T minus 1 times T minus Q.
So large V, yes, large V is this. So I get this.
That's two pieces of data there.
Yes.
Then you have two pieces of data for small v. V goes.
Okay, but
V
I
goes
don't
to
need
minus
I
infinity.
don't need to repeat it because it would give something similar.
I'm sorry.
Yes.
So two pieces of data for small t
T, yes, very good. So
And
small
two
t is here.
and two pieces of data for large t.
Exactly,
So
yes.
6 pieces of data.
Yes.
And so if I counted the coefficients of the polynomial, there should have been 7.
Very good.
And 7
Thank you.
minus 6 is that one and b.
Yes. But before I did this counting for you and I told you how many external things we have, these are masses and Q's, and how many internal things, and this will be the phases, and we expect that this is something that related to the Coulomb branch parameter, so this should be related to that.
How did you get to 7?
I was just guessing because she said there was 1.
No,
Let's
he
check, let's
he
check.
did correct, yes.
Let's check.
With fingers, yes.
So there's v squared t squared, there's vt squared, there's 1 times t squared, then there's, so we've done everything with t squared.
Yes.
Now there's tv squared, there's tv, and there's t, and then there's nothing. Constant, so 7.
Yes.
Yeah. Right.
So maybe this is a natural, so with this equation, maybe this is a natural place to stop and we can talk more